In this video, we'll be looking at Chapter 2 of Head-First Design Patterns, subtitled Keeping Your Objects in the Know. As with most chapters in this book, we start out with an application that we would like to build. In this case, we want to create a weather monitoring application for a company called Weather-O-Rama. Now, Weather-O-Rama already has a weather station set up, and at that weather station they have various sensors: a temperature sensor, a humidity sensor, and a pressure sensor. What our software needs to do is implement a weather data object that pulls weather data from the station and updates 3 different display elements with the new information. So here's our task list. It gives the specific displays that we need to update. 1, current conditions, 2, weather statistics, and 3, forecast. And we're using the weather data object to perform these updates. Specifically, we need to implement a method in our weather data called MeasurementsChanged. This method will do the updating of our display elements. Additionally, we need to implement 3 display elements that are updated each time the weather data has new measurements. This is our first attempt at a design. In our MeasurementsChanged method, we simply get the temperature, humidity, and pressure from the weather station. We make sure that our display elements all have a method called update that takes 3 values: the temperature, the humidity, and the pressure. Okay, it's time to analyze this initial design. I think that most of these assertions are self-explanatory, so we don't have to go over what they mean. Like the assertions in Chapter 1, these are potential problems with this design. So we want to see which of these problems our design has. Please pause the video and decide which assertions about our current design are true. Ready? Let's go through them one by one. First, are we coding to concrete implementations rather than interfaces? Well, in the method MeasurementsChanged, we are using objects current conditions display, statistics display, and forecast display. These objects are definitely coming from specific display classes, not from some general interface. So, yes, we are coding to concrete implementations rather than interfaces, and this is a problem. Second, if we add a new display element to our application, do we have to alter code? Well, yes, we do. Specifically, we have to add another line that calls the update method on the new display element. Next, is it true that we cannot add or remove display elements at runtime? Yes, this is also true. We're declaring these 3 display variables somewhere in our weather data class and using them in the MeasurementsChanged method. We can't add or remove another one at runtime. In the next column, we have an assertion saying that the display elements don't implement a common interface. Is this true? Well, it certainly looks like they all implement the method updates, which takes 3 values: temperature first, then humidity, then pressure. So from this perspective, they do seem to implement a common interface. Now that doesn't mean that a Java interface necessarily exists for the update method, but based on what we see here, it wouldn't be difficult to create one. Next, have we encapsulated the part that changes? Well, what is the part that changes? The other assertions kind of hint at this. It sounds as if we might want to add different display elements to our application in the future, and have them be notified when something changes. And if that's the case, it means that the number of objects that are potentially updated may change. And we certainly have not separated that part of the code and pulled it out of the weather data class. So this one is true. Finally, are we somehow violating encapsulation of the weather data class? Okay, perhaps this one deserves some explanation. We are violating encapsulation of a class when we expose private data to a client of the class in such a way that it can be modified. That's also known as exposing the rep and content coupling. So the answer is no, we're not doing any of that here. To solve the problems with our design, we're going to use the observer pattern. Sometimes it's easier to think of this as the publish-subscribe pattern, and in fact, some people do call it that. In the observer pattern, you have a subject object. The subject object has data or information that is periodically updated, and the observers want to know about these updates. This is similar to subscribing to a magazine. The subject object is the publisher of the magazine, while the observer objects are subscribers to the magazine. The subscribers are essentially saying that they want to receive the new edition of the magazine when it's published. In order to do this, the publisher just needs to mail the magazine to its list of subscribers. The only thing that a publisher needs to know about its subscribers is where to send the magazine. Subscribers can unsubscribe at any time, and those who are not subscribers can subscribe at any time. Here's a description of the observer pattern. It defines a one-to-many dependency between objects. The publisher is the one and the subscribers are the many. When the object changes state, all of its dependents are notified and updated automatically. In other words, when the publisher has more information to publish, it sends the information to its subscribers. Here's a design principle that's very relevant to this pattern. Strive for loosely coupled designs between objects that interact. Now, objects that interact are, by definition, already coupled. What this principle is saying is that those objects should be as loosely coupled as possible, meaning that they know as little as possible about one another. So loosely coupled objects do interact, but they have very little knowledge of each other. Loosely coupled designs can handle change easier because they minimize the interdependency between objects. It makes sense that loose coupling is better than tight coupling because, in general, coupling is something that we want to minimize. Here's a class diagram for the observer pattern. The only thing that a subject or publisher knows about its observers or subscribers is that they implement the observer interface, which contains the method update. The only thing that the observers know about the subject is that they can register with the subject and remove themselves from the subject's list, and that the subject will notify them by calling their update method when something important happens. Looking at the diagram, the reason we have loose coupling in this design is because of the interfaces. Everything the subject knows about an observer is what is available through the interface. In the diagram, the concrete observer does have access to the concrete subject, but this doesn't have to be the case. Here's the class diagram for our specific weather monitoring application. The displays are observers, and the weather data object is the subject. The display objects register with the subject and are notified via a call to their update method when the data changes. The registered observers are simply stored in a list structure, and when the observers need to be notified about a change in the data, the subject simply iterates through that list and calls the update method for each observer. Java makes heavy use of the observer pattern in its GUI components. Observers are known as event listeners or just listeners. And individual components, like buttons for examples, are subjects that other objects can listen to. For example, when buttons are clicked, they send out action events to all of their listeners. An action listener must have an action performed method that takes an action event as an argument. And when it receives the action event, it executes the code, like, for example, updating the text in the graphical interface. And that's it for the observer pattern. In the next video, we'll look at the decorator pattern.